Your electric car has just one gear. Not two, not seven. One. A Ferrari has 7. A Volkswagen Golf has 6. A truck has 10. Your Tesla has 1. And it doesn't need any more. Because the motor spinning your wheels operates on completely different principles than any combustion engine ever built. It has no idle, no power band, no stove, no rev limiter that matters in practice. Understanding the EV motor is understanding the single biggest reason electric cars feel so different to drive. Today we open it up. Over the last 4 weeks on WattInside, we've walked through the anatomy, the battery, the BMS, and the inverter. Today, the component all of that was leading to. The thing that actually converts electrical energy into physical motion. Let's start with the fundamental question. Chapter 1. What is an electric motor? At its core, an electric motor is a device that uses magnetism to create rotational force. You send current through a coil of wire. The current generates a magnetic field. That field pushes or pulls against another magnetic field. Rotation happens. Every electric motor since Michael Faraday built the first one in 1821 has worked on this principle. Whether it's the tiny motor in your electric toothbrush or the 200 kilowatt monster in a Tesla Model S Plaid, what changes between motors is the geometry, how the coils are arranged, where the magnets are placed, whether the magnets are permanent or generated by more electricity. Modern EVs use one of two main types, and the choice matters a lot. Chapter 2. Permanent Magnet Synchronous. This is the type used in the Tesla Model 3, the Model Y, the Hyundai Ioniq 5, the Ford Mach-E, the Kia EV6, and most modern EVs. The name is a mouthful, but the concept is simple. The rotor, the part that spins, has permanent magnets embedded in it. The stator, the stationary outer part, has coils of wire. When you send precisely timed AC current through the stator coils, it creates a rotating magnetic field. The permanent magnets in the rotor are pulled around by this rotating field, perfectly synchronized. Hence the name. The advantages are massive. Very high efficiency, especially at low and medium speeds. Compact size, excellent torque density. The disadvantage is the magnets themselves. They're made from rare earth elements, mostly neodymium, praseodymium, and dysprosium. And rare earth mining is dominated by China. Over 90% of processed rare earths come from Chinese refineries. This is a geopolitical vulnerability for every Western automaker, which is why some, like Tesla, are actively working on rare earth-free motor designs. Chapter 3. AC Induction Motors. The alternative type. What Tesla used exclusively in the original Model S and Model X for years. Here, the rotor has no magnets at all, just conductive bars of aluminum or copper arranged in a squirrel cage pattern. When the stator creates a rotating magnetic field, that field induces electric currents in the rotor bars. Those induced currents create their own magnetic field, and the two fields interact to pull the rotor around. The key word is induction. The rotor's magnetism is created by the process itself. There are no permanent magnets to buy, no rare earths to source. The advantages are ruggedness and cost. Induction motors are simpler to manufacture. They handle high loads and high speeds better than permanent magnet motors. And they don't lose efficiency dramatically when running at very high RPM. The disadvantage is efficiency at low speeds. An induction motor is slightly less efficient than a permanent magnet motor when cruising at 50 kilometers per hour. That translates to slightly less range. This is why Tesla eventually put a permanent magnet motor in the rear of the newer Model S and X, keeping induction only in the front. Best of both worlds. High efficiency during normal driving from the rear. High power delivery for acceleration from the front. Chapter 4. Why only one gear? Back to the opening question. Why does your EV have only one gear? Combustion engines have a very narrow useful power band. A gasoline engine typically makes peak torque at around 3,000 to 5,000 RPM and peak power at around 6,000. Below 1500, it barely produces useful power. Above 7000, it starts destroying itself. To use this narrow band across a range of vehicle speeds, you need a gearbox. First gear for launching, second, third, and fourth for city driving, fifth and sixth for highway efficiency, sometimes a seventh or eighth for overdrive. Electric motors have no such constraint. An EV motor produces maximum torque from 0 RPM. From standstill, it maintains high efficiency across the entire operating range, typically from 0 to 18,000 RPM. That's more than double the range of a combustion engine. So instead of a multi-speed gearbox, you have a single fixed reduction, usually around 9-to-1. The motor spins 9 times for every 1 revolution of the wheel. That single ratio handles everything from crawling in traffic to 200 kilometers per hour on the highway. Fewer parts, less mechanical loss. No shifting velay, no jerk, just smooth, continuous acceleration from 0 to top speed. This is why an EV feels so different to drive. It's not just the instant torque, it's the absence of gear changes entirely. Chapter 5. 2 motors, 3 motors. For motors, a combustion car has 1 engine. That engine sends power to a differential, which splits it between wheels. An electric car can have any number of motors, and each motor can be independently controlled. Single-motor EVs typically drive 1 axle, usually the rear. Dual-motor EVs put 1 motor on each axle. All-wheel drive with no mechanical connection between front and rear. The car's computer decides how much torque each motor produces at each instant. Better traction, better stability, better efficiency, because in most driving conditions the rear motor does almost all the work while the front idles. Tri-motor EVs, like the Tesla Model S Plaid, put 2 independent motors on the rear axle. This enables torque vectoring. The car can send more power to the outside wheel during a turn, effectively steering with the accelerator. Quad-motor EVs, like the Rivian R1T, put a separate motor at each wheel. Maximum control, maximum complexity. You can literally spin 1 wheel forward and 1 backward, allowing the truck to turn place. It's called tank steering. None of this is possible in a combustion car without extremely complex mechanical differentials. In an EV, it's just software controlling 4 motors. Chapter 6. Why motors fail. Electric motors are the most reliable component of your EV. They typically outlast the rest of the car. Tesla motors have documented cases exceeding 1 million kilometers, but they do fail sometimes. And when they do, the failure modes are specific. Bearing failure is number 1. The bearings that let the rotor spin are mechanical parts that wear over time. High mileage motors sometimes need bearing replacement. It's expensive but doable. Insulation breakdown is number 2. The coils in the stator are wrapped in insulation. Over years of high voltage exposure, that insulation can degrade. When it does, the motor short circuits and dies. Water ingress is number 3. Motors are sealed, but seals wear out. Water inside a spinning high voltage motor is catastrophic. Replacing an entire motor typically costs between $5,000 and $15,000. Many manufacturers sell you a complete drive unit, including inverter, motor, and reduction gear. Because the components are so tightly integrated, they don't do partial repairs. Here's something I want to point out. For over 100 years, cars have been defined by their engines. Horsepower, torque curves, red lines, displacement, number of cylinders. The engine was the personality of the car. In electric vehicles, the motor is almost never mentioned. Nobody buys a Tesla for its motor. They buy it for its battery, its range, its software. I think this is wrong. The motor is what determines how a car actually feels when you drive it. The instant response of a Tesla Plaid, the smoothness of a Model 3, the aggressive launch of a Porsche Taycan. All of that is the motor, not the battery. We just aren't used to thinking that way. But we will be. In 10 years, motors will be a spec people talk about again, just for very different reasons than they used to. So to recap, your EV motor is the reason you don't need multiple gears. Because it produces peak torque from zero and maintains efficiency across a huge RPM range. Two main types dominate. Permanent Magnet Synchronous, more efficient but needs rare earths. AC Induction, simpler and rare earth free but slightly less efficient. EVs can have 1, 2, 3, or 4 independently controlled motors. This unlocks capabilities no combustion car ever had. Torque vectoring, tank steering, precise per wheel traction, and motors are the most reliable component in modern EVs. They typically outlast everything else. Next week, we go into thermal management, the system that keeps every component in this series alive. Why some EVs preheat their battery on the way to a supercharger, and why cold weather kills your range more than you think. If you found this useful, subscribe. Drop a comment with what surprised you most about EV motors. I read all of them. See you Wednesday.